Does that mean you've been down in Mount Erebus?
Not yet, but actually I'm waiting for word on a grant that will take me down to Antarctica, not this coming winter, but the following year, hopefully. So fingers crossed, everybody, for that. Can everybody hear me okay? No. Louder. Okay. How's that? Better? Okay. So thank you all so much for coming tonight. It really is a pleasure for us to have so many of our neighbors come and visit us and hear about what we do, especially on beautiful evenings like tonight. So as Rick mentioned, I'm going to talk to you a little bit about some of the work I do and work that's being done in my field of volcanology. I just want to set the tone for this talk with a few slides about the focus of this talk. I'm not really going to be talking today about volcanic eruptions. I'll spend a little bit of time on volcanic eruptions, but basically as a context for the real thing that I want to get to, which is the secret life of quiescent volcanoes. So this is Mount Etna back in the fall of last year. It had a beautiful eruption sort of overlooking the city of Catania here on the island of Sicily. This is spectacular activity. It's a very active volcano, and one of the places that I and some of my volcanology colleagues here at DTM have been working. I'm also not going to talk about these guys. And actually, hopefully, what I would like to do tonight is actually change your mind about a volcano that you might hear described as inactive, or you might think is inactive when you just look at it and you see that it's not erupting. So what I'm going to really try to focus on and teach you about tonight are volcanoes that are somewhere in between these two end members. And the big point that I want to make in this talk tonight is that eruption, which we tend to focus on because eruptions are beautiful and they're dangerous and they're interesting, is really just one end member phenomenon of an entire continuum of natural processes that occur in volcanic areas. And actually there's a lot going on in the in-between stages between a volcano that's totally quiet and a volcano that's in full-blown eruption. And this is where actually most of my research occurs and where I think we learn quite a bit about how volcanic systems work. So the point here is that this is basically the sequence toward eruption, very cartoony of course, but that prior to an eruption you have magma that moves from somewhere deep in the earth up into the Earth's crust. It may stall out at some point in the mid-crust. The volcano may reflect this sort of residual magmatism or deep magmatism at the surface with some degassing activity, maybe a little bit of seismic activity, but it's basically just sitting there being mostly harmless. As that magma continues to pressurize and ascend, the surface expression gets a little bit stronger. We may actually get to the point shortly before eruption where we see maybe some gas explosions, and then eventually this process culminates in an explosion. So the point is that a volcano does not necessarily have to continue all the way from 1 to 5. It can stop at really any point in this sequence. And in fact, most episodes of volcanic unrest do. We're not at the point yet where we can really quantify how often this sequence culminates in eruption, but the evidence is really starting to suggest that in most cases, magma stalls out somewhere in the crust before it gets to the surface and erupts. So the bulk of Earth's shallow magmatic activity is really in this middle realm here, and eruptions are really probably a somewhat rare end member that we tend to focus on because A, we see them more readily, and also because they're what impacts us most strongly. Okay. So the way this talk is going to go, the focus of course is on volcanoes that are not erupting, but to talk to you about volcanoes that are not erupting, I want to first tell you a little bit about what we see when we do see an eruption and why we monitor volcanoes in the ways that we monitor volcanoes. Obviously, one of the key reasons to monitor a volcano is to know in advance that it is going to erupt. So I'm going to talk to you a little bit about historically how volcanoes have been monitored, and also currently the modern paradigm of volcano monitoring. I'll give you an example of what it looks like from a geophysicist's perspective before a volcano erupts. As Rick said in the introduction, one of the great things about volcanoes is that they do tend to warn us. Usually if we have the right instrumentation on the volcano, we get anywhere from hours to months of warning that an eruption is coming. And most eruptions at well-monitored volcanoes are successfully forecast. So I'll show you what that looks like. And then the second half of the talk, I'm going to talk about the quiescent volcanoes, the ones that aren't really doing anything at the surface, but are doing actually quite a lot when you put instruments on them and start to understand what's going on below the surface of the Earth. And then I'll finish up by telling you some of the implications of what we've seen so far and what we really need to do going forward to understand the problems in volcanology and in volcanic monitoring. Okay. So to start with some notes on historically how volcanoes were monitored. Before the past few decades where we had the widespread advent of instrumentation on volcanoes for monitoring, it was pretty easy to say volcano was in either state A, it was not erupting, or state B, it was erupting. Basically what you got was what you saw at the surface. But that's not entirely true, because in some cases, especially before large eruptions, even if you have no instrumentation, there are things that you can sense or feel before an eruption. So one of the most intriguing and earliest examples of this comes from the 79 AD eruption of Mount Vesuvius, which is famous for destroying the cities of Pompeii and Herculaneum, and also a fairly bad movie that came out recently.
Really bad.
but I'll admit it, I saw it and I enjoyed it. So this was a very significant eruption. It was actually a rather large eruption, very destructive eruption. But to the volcanologist, one of the interesting things about this eruption is that Pliny, who was a naturalist and a lawyer and a sort of jack of all trades, wrote a couple of very detailed, very beautiful letters in about 25 years following this eruption, giving an unprecedented amount of detail on what he had observed prior to and during these eruptions. And this really is an incredible wealth of information for us for this type of eruption. An eruption of this scale is relatively rare, so any information that we as scientists can get from written records like this gives us very important information. And so I excerpted one, I think, the money quote from the first letter that Pliny wrote about this. And what it says, loosely translated, I apologize to anybody who speaks actual Latin, is this eruption was preceded by several days of earthquakes. So that, the first part of the sentence is actually quite interesting, because there were felt precursors. But the second part of the sentence goes on to say, the people of the region Campania were not very concerned because this was a fairly common event to them. So this is something just to keep in your mind for later. But for now, basically what he tells us is that this eruption was actually, there were signs that it was coming. There were earthquakes that were occurring prior to this eruption for days before it started. So even though there were no instruments, there were precursors. And this was the type of warning that you would get beforehand. Similarly, one of the largest eruptions of the 20th century, the 1991 eruption of Mount Pinatubo in the Philippines, was instrumentally monitored, but it wasn't until some of the local villages, the people who were living high up on the slopes of this volcano, sent some of their ambassadors, in fact a nun, down into the city nearby to basically tell scientists, look, we're feeling earthquakes, we're starting to smell some sulfur gas, that people became aware that something might be going on, and they started making efforts to bring instruments. So actually the very first sign that Mount Pinatubo was getting ready to erupt was these felt earthquakes, these signs that people just living very close to the slopes of volcanoes were noticing, and then were reporting to scientists so that the instrumentation could then come in. So this is volcano monitoring without instruments. It is possible. It tends to be the larger eruptions. This was a very large eruption, as was Vesuvius, that give these felt, these sort of observable surface signals. Many eruptions, especially the smaller ones, you really need modern instrumentation to detect the signals because they're very, very small. Okay, so that brings us on to modern volcano monitoring. So the way that volcano monitoring is done currently is usually very remotely from the volcano itself. So in most cases, the instruments are placed on the volcano, and the data are sent by radio or phone or satellite in some cases to a remote observatory for processing and interpretation. So the focus is often on monitoring volcanoes that are kind of in the middle of nowhere. Nobody's living out there, nobody's close enough to feel if there are earthquakes, to smell if there's gas, to notice if there are any changes in the natural environment. Just as an aside, so I wanted to mention actually the American Volcano Observatory System largely constitutes 3 observatories right now. The Alaska Volcano Observatory in Anchorage and Fairbanks, where I do a lot of collaborative work, the Cascades Volcano Observatory, and in fact the oldest volcano observatory in the United States and one of the oldest working volcano observatories in the world, the Hawaiian Volcano Observatory. The Hawaiian Volcano Observatory was actually started in part by a research associate from our neighboring department here on campus, the Geophysical Lab, in 1911. So Carnegie has a very, very old and long-standing tie to volcano monitoring. We were one of the founding groups for the Hawaiian Volcano Observatory. Okay, so why monitor a remote volcano? Why bother? If it's out in the middle of nowhere and nobody's around to feel the precursors, why should we care about the eruption? Well, this goes to the way that modern volcano hazards differ from early volcano hazards. The impacts of a volcanic eruption, even a moderate one, are now very much global. So the hazard may be to people that are on the ground living around the volcano, but there is an equal and often larger hazard to aircraft. So we're very interested in remote volcanoes, especially remote volcanoes that are located along major flight paths, because eruptions at those volcanoes can affect aircraft in very severe ways. And this was really brought to the fore of our attention in 1989 during an incident that occurred during actually a fairly small eruption of a volcano called Redoubt in Alaska. It's about 150 kilometers outside of Anchorage. It erupted a few years ago, a second time. It was not a particularly remarkable eruption from a volcanological standpoint, but right as the eruption was occurring, a KLM jet at 747 was flying into Anchorage Airport and encountered this ash cloud and lost all 4 of its engines. It was an absolutely terrifying and, in fact, unprecedented event. Boeing did not realize that one of these 747s could actually lose all 4 engines because the plane had been designed so that those systems would be independent. But the plane lost all 4 of its engines. It went into a 4-minute glide and fortunately was able to restart its engines and come to a landing at Anchorage International. There was a lot of damage, millions, tens of millions of dollars of damage to the plane. But more importantly, this incident really brought to our attention the need to monitor remote volcanoes. So the Aleutian volcanoes in Alaska are some of the most closely monitored volcanoes in the United States. And the Aleutians are this little chain of islands that extends out into the northern Pacific from Alaska. Okay, so kind of middle of nowhere. There are villages out here, but it's very remote. There aren't many people living out there. But what occurs in this area, and the reason that so many resources and so much attention is focused on these volcanoes, is that this is one of the most heavily trafficked air corridors in the world. So this is called the NOPAC, Northern Pacific Corridor. Any of you taken a flight from Washington, D.C. or New York City to Tokyo or Beijing? Yeah, I see some hands. You've flown right over these volcanoes, as well as these volcanoes on the Kamchatka Peninsula, as well as these volcanoes in the Urals. So when you take a direct circle route from the east coast of the United States to anywhere in Asia, you're going to go up and over very far north to take the shortest direct route, and you're going to fly over all of these potentially very active volcanoes. So it's extremely important to watch these volcanoes 24/7, even though they're so remote, because an explosive eruption at one of these volcanoes could put ash high enough to interfere with an overpassing aircraft and very quickly do a lot of damage to that aircraft. So right now, about 10,000 people a day fly over this area, and even more, so 60,000 aircraft. A lot of it is actually cargo. So this is a very heavily watched corridor in terms of volcanic monitoring. There are systems set into place to avoid incidents like the Redoubt 1989 incident. Now there's almost global coverage for volcanic ash monitoring by a series of offices known as VACs, the Volcanic Ash Advisory Centers. We have one in Washington, D.C. actually, which is responsible for the continental U.S., Central America, and parts of South America. So basically this is a 24/7 staffed office whose job it is to watch for ash clouds and then immediately issue warnings, SIGMETs, notices of significant meteorological activity to the various agencies like the FAA so that planes can be diverted or flights can be stopped in the case of a volcanic eruption. So this is a very good system. It works quite well and in terms of avoiding ash aircraft encounters. One of the main ways in which this is done is using satellite data. So how do we actually see an ash cloud in the Earth's atmosphere? Well, we have various satellites with instruments on them that allow scientists to basically look for ash in the atmosphere. So this is basically identifying a volcano that already is an eruption. By looking for ash, you're not going to see the volcano before it erupts. You're going to see once the ash is in the atmosphere. And it's pretty effective. So just as an example here, this back picture, here maybe if you squint, you can see this little wisp here. And then if you kind of zoom out, you'll notice that this is South America. This is the lower part of South America. This is a volcano called Chaiten in Chile. It erupted in 2008. It was actually a fairly large eruption. And this ash cloud was picked up on one of the weather satellites, actually, the GOES-12. So this is a geostationary satellite. This is another example. This is an instrument called the AVHRR. It's a satellite that orbits a little bit closer down to the Earth, a lower orbit, so it can actually see smaller things. But because it's in orbit, it's not geostationary. It doesn't look 24/7 at all places on Earth. But this example shows an ash cloud. You can see it very faintly here, and then after some processing, very brightly here, from an eruption of an Alaskan volcano in 1992. So we're pretty good at detecting even fairly moderate amounts of ash in the atmosphere, even from fairly small eruptions, once the eruption gets going. But ultimately, what we would want to know, what we prefer to know, is beforehand that a volcano is getting ready to erupt. And this is where the bulk of volcano monitoring occurs. We want to see the eruption coming, and volcanoes will generally give us warnings that an eruption is coming if we instrument them. So I'm just going to go through briefly the main types of technologies that we use to monitor volcanoes. There are lots more that I'm going to mention, but these are just three big ones. So one thing we can look for is an increase or a change in the composition of gases that are coming out of the volcano. And the main gases that we monitor are CO2, carbon dioxide, and SO2. So we can use either ground-based, so here we have a SO2 camera, aircraft-based, so often we'll duct tape these onto the side of a helicopter and go fly the helicopter around to take a sniff of the volcano to see if there are changes. So usually we just get a little time series like this. So this is Mount St. Helens, the amount of SO2 in tons per day going through the 1980s, and you can see the 1980 eruption, there was a big spike in SO2. So when we have this information, it's fairly clear if the volcano is putting out SO2. This is something that changes very dramatically before and during an eruption. So this is one of the things we watch for. We can also do it from space. We can do it from satellites. This is the TOMS instrument, which is actually an ozone mapping instrument, looking at an SO2 plume from a volcano in Papua New Guinea that erupted in 1994 called Rabaul. However, this is a much lower resolution. So this one, the satellite-based instruments and satellite-based instruments in general can only detect very big things. So we can't get the sensitivity that we can from satellites with the ground-based instrumentation. But what we can get with satellite-based instrumentation is global coverage. We don't have to actually go boots on the ground to the volcano with our camera and our helicopter and do the work. We can just let the satellite pass over. Another major tool that we use to monitor volcanoes is monitoring of ground deformation. So we can see very, very subtle changes in the height of the ground as magma moves up into a volcano, it basically displaces the rock and causes the volcano to swell. And that swelling can be very, very small, on the order of millimeters. In some cases, if it's a very large eruption or magma is very close to the surface, we can see up to meters of displacement. You can see it with the naked eye. But in most cases, you need to do it instrumentally. It's very, very subtle. But we can see it. So we have two common tools for doing deformation monitoring on volcanoes. The first is GPS. So this is a GPS receiver. It's basically talking to the GPS satellite constellation, the same as the thing in your car that tells you how to get to Whole Foods. We just have a slightly fancier version of that, but it basically tells you the exact coordinates of this position, and then if you either leave it there and watch it over time, or if you come back a week or two later and measure the exact same spot, there's a benchmark down on the ground here. You see that it's changed, either it's scooted over a little bit or it's gone up a little bit. That gives us very, very high resolution, so on the order of millimeters. So here below, you're just seeing an example from Long Valley Caldera in California of a GPS line. So this is actually the distance between two GPS stations, showing an increase in the distance. So the volcano is swelling up, and we can see that really nicely. And the order here is millimeters. So very, very sensitive to very small changes in the position of the ground. We also have satellite-based tools that allow us to look for deformation. Again, they're a little bit less sensitive because they're satellites, but again, the nice thing is we get global coverage, so we don't have to go out with the helicopter and the car batteries to do this. SAR is a slightly more complex technique, but basically the way it works is the satellite makes a first pass, snaps a picture that does a very high resolution measurement of the ground topography, so the shape of the ground, does a lap around the Earth, comes back around sometime later on, and snaps the exact same picture a second time. And then by subtracting those two pictures, we can get a map of how the ground has changed between those two satellite passes. So with this technology, we can get deformation resolution on the order of centimeters. And again, the nice thing is that we can do this pretty much any volcano on Earth. There are some limitations, but it's a much more global tool. It's just a little bit less sensitive.
What about strain meters?
And I would be remiss without mentioning strain meters. So strain meters, thank you. He was not a plant, I swear. So I would be remiss without mentioning strain meters. And as I said, we have other technologies. I'm just mainly touching on the ones in most common use. But we've got other tools for doing all of these measurements. And one of the tools that is used for deformation was developed here at DTM by my colleagues Alan Lindy and Selwyn Sachs. It's called a strain meter. It's a very sensitive instrument that's put down actually in a borehole. So here you can see the drilling rig. They're boring into the ground. That picks up very, very minute changes in strain or deformation in the Earth. And this is an incredibly sensitive instrument. It's able to see signals at volcanoes that our other instruments can't. It's a very specialized tool, but it has been instrumental in successful eruption forecasts at volcanoes where the other tools that we have were just not sensitive enough to pick up the precursory changes. And this is something that's been developed at Carnegie and exists on several key important volcanoes worldwide. And they are still being installed on volcanoes in Iceland and Italy, in fact, this summer, I believe. Okay, and the final thing I want to mention, this comes to what I do, is seismic monitoring. And seismic monitoring is probably the most common way of monitoring a volcano. So for historical reasons, if a volcano is instrumented, it's usually got a seismometer on it. And this is what I do. I tend to look at seismic data from volcanoes. This is what they look like in the field. They're not very exciting. Unlike Alan, I have to dig my own holes. I don't get fancy drill rigs to do it for me. So I have practical skills. I'm very good with the shovel. But we take these things out and we bury them. And they're very sensitive to very tiny earthquakes. So these are earthquakes that you wouldn't be able to feel. In fact, many of them have negative magnitudes on the Richter scale. The largest ones usually have something like a magnitude 1 or 2. So these are tiny, tiny earthquakes that we can't feel, but our instruments can pick up. And I've actually got up front here, if you want to come up after the talk and have a look, I've got one of our instruments out here and set up just so you can kind of see what these things look like and what I have to strap onto my back and carry up a volcano to get my data. So when we get seismic data from volcanoes, there are a lot of different things we can do with the seismic data, but I'm just going to teach you some of the basic things that we look at that are where a lot of our information comes from, especially when there's a crisis situation and we need to make decisions very quickly about what is likely to occur at the volcano. So the simplest thing we can do is just count earthquakes, and in fact this is an incredibly rich piece of information for us, earthquake rates or earthquake counts. So here you're looking at an example of raw seismic data. So this is just time here, and then this is the displacement on the seismometer. So it just kind of scoots along, and when there's an earthquake, the amplitude of the displacement goes up, so you can see some individual earthquakes in here. And we can count these. So throughout the rest of the talk, I'll either show you these raw seismogram plots, and you can just see by eye changes in the rate of these little bursts, these little earthquakes. Or I'll show you sort of binned counts, like number of events per hour over time. But this is actually it's a very simple tool, but it's one that we get a lot of information from. Another thing that as volcano seismologists we look at in earthquake data is the frequency content of the earthquakes. So by frequency content, I mean, is it a high-pitched wiggle or is it a low-pitched? So this below here is called a spectrogram, and it's a plot, again, in time. But instead of the displacement, this is the frequency. So these are the low frequencies. These are like the deep booming frequencies. If you were to play one of these signals, it would sound like Barry White. And if you were to play one of these, it would sound a little bit more like me. And actually, there's a lot of information to a volcanologist in whether the volcano is speaking in a high-pitched voice or a low-pitched voice. And actually the low-pitched voice is what makes us a little bit more nervous. Volcanoes, on average, tend to go to lower frequencies in their seismicity the closer they are to eruption. So we're always looking for changes in the frequency of our signals. And so I'll show you some of these types of plots and talk about the frequency content of the signals in some of my examples. And then, of course, the other things we look at, locations, depth. So this is just a cross-section. So here's depth versus latitude. This is Mount St. Helens. So how deep are the earthquakes? How close are they to the surface of the Earth? Also, what magnitude are they? Are they big earthquakes or tiny earthquakes? How much energy is being released? So this is kind of the basic information that we get out of this data. Okay. So before I move on to the quiescent volcanoes, I just want to show you one quick example of what it looks like before a volcano erupts. And there are certainly lots of different patterns, but this is kind of a classic one. This is maybe the most typical type of thing that we see. So this is Mount St. Helens in 2004. Mount St. Helens was an eruption. Of course, everybody knows very famously the 1980 eruption of Mount St. Helens that actually went on through 1986. But Mount St. Helens erupted again between 2004 and 2008. It was an extremely well-monitored eruption. We learned quite a lot from that data set. The eruption was forecast, but there were some surprises in it as well. So on September 23rd of 2004, the volcano was kind of sitting there doing business as usual, maybe 1 or 2 pops a day, earthquakes. And then late on the 23rd and into the 24th, it started having a little bit of unrest, seismic activity. I actually got an email from one of my buddies, Seth Moran, who's the seismologist at the Cascades Volcano Observatory, saying, "Oh, cool, we're having a little swarm at St. Helens. This is fun." Little did he know what was about to happen to his life. So, it went on for about a day, and it looked like it was starting to quiet down again. So CVO put out an information statement saying, swarms are not uncommon. We're watching it closely. So far, it doesn't look like precursory to an eruption, but we are keeping an eye on it. It is an elevation in the rate of seismicity, but these are all high-frequency earthquakes. It's not unusual for the volcano to go through these small swarms periodically and then quiet back down. Fast forward. A few days later, after some quiescence, the seismicity started back up again. And this caught CVO's attention because not only was the seismicity rate increasing again, but the frequency content of these earthquakes was now getting lower. So they were starting to see low-frequency earthquakes. So they actually changed the alert level. So observatories use a very simple color code, red, green, or yellow, red, to indicate the level of concern. So they actually put Mount St. Helens at a warning here because the rate of seismicity was going up and because the frequency content of the earthquakes was changing to lower frequencies. And Once they did this, they continued to see this, and then it very suddenly increased. Started to get much more intense. Started to get even more intense a few days later, and in fact, they started to do some helicopter overflights to do visual observations, and they observed actually some surface deformation. So this is the glacier on the side of the 1980 to 1986 dome at the top, and they saw that the glacier was starting very rapidly to be broken apart, like it was being pushed and pulled by something. So in fact, the alert level went up one more step to orange, which was basically warning. So an eruption appears to be imminent. So they caught this on September 29th. And then on October 1st, the first explosion was observed. And Mount St. Helens then continued to ramp up its explosive activity over the next few weeks, and then began to settle into a steady state eruption that lasted almost 4 years. So this is a very classic example of what we see in seismic data before an eruption, how we use that information to forecast the eruption. Okay? It doesn't always go this perfectly, but this is kind of what we tend to expect from a volcano. Just as a side note, so seismic data is, of course, extremely useful. I hope I've now convinced you of that for understanding what the volcano is going to do. But there is a downside to seismic monitoring of volcanoes, and that's that volcanoes are not very friendly environments for very sensitive technologies. So one of the best seismometers, one of the ones that was closest to the summit, September Dome, was destroyed during that October 1st explosion. So this is a before and after shot. And this is not atypical. Usually, as soon as the activity starts, a lot of the network is actually destroyed by, in this case, falling rocks or ash coming down, raining down, and breaking out the solar panels. So as soon as the eruption started, there was all of a sudden a critical loss of information. And this is a fairly common problem with eruptions. And the problem with monitoring volcanoes technologically, that they're harsh environments. It's very hard to operate these instruments on volcanoes, even when they're not erupting. There are gases, there's snow. The elements are not very nice to these instruments. And then, of course, eruptions are very, very destructive to these sensitive instruments. Okay, so now for the second half of the talk, I want to move on and start talking about these non-erupting volcanoes. And I'm basically going to show you 4 examples. Different types of unrest, not unlike what I showed you for Mount St. Helens, but in all of these cases there was no eruption. In fact, none of the volcanoes I'm going to show you, well, that's not entirely true, but in all of these cases this is unrest that does not culminate in eruption. So I'm just going to step through these, and then at the end I'll sum it up and talk a little bit about some of the problems that we have in dealing with volcanoes, because we don't always see unrest culminate in eruption. What this means, what we might do to get better at understanding the processes that lead to these sort of failed events, these false alarms, and how we can differentiate them from events that do proceed to eruption. Okay, so example number 1 is maybe from a slightly surprising place for you guys, Lake Tahoe, California. This is in the Sierra Nevadas, Northern California, on the California-Nevada border, and it's not an area known for volcanic activity. In fact, this has not been a volcanically active area for millions of years. Yet, in 2003, some seismometers that were operating in the area as part of a larger scale seismic experiment picked up this very strong increase in small micro-earthquakes. These were all high-frequency earthquakes centered beneath Lake Tahoe. And we call this a swarm, so it's like a little swarm of bees, and then it dissipates. This swarm lasted a few months. It was very unusual for this area. This was not something that was expected, nor something that's typically seen in this part of California, because it's not volcanic, and these earthquakes looked very volcanic. So they were centered here beneath North Lake Tahoe, and they were actually quite deep. So they were about 28 to 32 kilometers below the surface of the Earth. This is quite deep. We usually, when we see seismicity beneath a volcano before an eruption, it's in the upper 10 kilometers of the crust. So this is unusually deep seismicity. But the fact that this was a little swarm of events, there was no main shock followed by an aftershock, It was very volcanic in nature. Fortunately, there was also one GPS instrument operating very nearby at this dot here called SLID. And coincident with the earthquake swarm, this GPS station started to move north and east and upward. So basically away from this swarm volume. So this point started to move outward, almost like the ground was swelling and pushing this point away. Okay? So this episode, all told, appears to be, and in fact it's very hard to explain otherwise, consistent with a deep intrusion of magma beneath Lake Tahoe. So this did not culminate in an eruption. We have seen this before. This is not the only example of swarm activity, deep magmatic unrest in an area where there is no volcanism. Often these deep swarms tend to pop up in slightly surprising places. They're not unprecedented, but they're quite rare, and they're not very well understood. We know that the Sierras have in the very, very distant geologic past been a volcanic arc, but we don't expect them to be volcanically active today. So this is a bit of a mystery as to why this is occurring, but we are pretty convinced that this is some magma intruding into the lower crust at about 30 kilometers. Okay. Another example, this is one of my favorite volcanoes. It's a very obscure volcano that nobody's ever heard of, but I find it a fascinating volcano because it frequently has little swarms of earthquakes that don't culminate in eruption, and it exists in a part of Alaska where all of its neighboring volcanoes are very, very active. So all of the volcanoes in this part of Alaska erupt on average about every 10 years. So Redoubt, which I mentioned earlier on, is this volcano's neighbor to the north. Redoubt erupted in '89, it erupted in 2009, so about a 10 to 20 year periodicity. And that's typical for volcanoes in this area, except for this guy, Iliamna. Iliamna doesn't erupt. It hasn't erupted, we think, for about 300 years. But about every 10 to 20 years, it goes through this very strong swarm of earthquakes. Again, these are all high-frequency earthquakes, but fairly strong, and we also see that the amount of gas, so this is SO2, the blue line here is SO2, we see that the amount of SO2 coming out of the volcano also spikes during these swarms. And occasionally, so the last one of these that occurred in 2012, we also saw that the glacier up on the summit of this volcano was melting very strongly, and there was a lot of gas coming out, steam, which suggests that there was heat that was in place beneath the volcano at fairly shallow levels. So it appears that this volcano, instead of erupting, periodically gets these shallow intrusions that get stuck. And these are fairly shallow. This is the 1996 swarm. Most of those earthquakes were, so the summit is actually 3 kilometers above sea level, which is why you're seeing the negative number here. They're very shallow, so just a few kilometers below the Earth's surface. So this volcano, for some reason, seems to have these sort of moderate events where things just seem to get stuck somewhere in the last few kilometers, and nothing comes out for some reason. Again, we don't know why, but at this point we're pretty convinced by the data that this is something that's occurring every so often at this volcano. Okay, another volcano, one where I spend a lot of time these days, that has a very different type of behavior, is called Tolica. This is another somewhat obscure volcano in Nicaragua. It is pretty much constantly active, seismically. So if you look at the summit, you'll see gas coming out. You see that this is a potentially active volcano. But when you put a seismometer on this volcano, it's just astounding the number of earthquakes that this volcano has. Not only the number of earthquakes, but also the fact that they're low-frequency earthquakes. Hundreds and hundreds of low-frequency earthquakes every day at this volcano over, as far as we can tell, years and perhaps decades. So we've been monitoring this volcano for 4 years now, and we've recorded close to 250,000 of these low-frequency earthquakes. Yet, so if you were to go to any other volcano, not knowing anything about the volcano, put a seismometer on that volcano, turn the seismometer on, and see this, you would panic. This is incredible. This is what it looks like just before an eruption. Yet this volcano, for some reason, is doing this continuously for years to decades. It's just simmering away right on the cusp of an eruption. Occasionally it does tip into eruption, very, very small eruptions. We were able to observe one in 2011. So this is a time series of the number of earthquakes. The blue guys are the number of low-frequency earthquakes, and the red guys are the number of high-frequency earthquakes. So you can see this is it's actually background behavior, it's normal behavior. These very high rates of low-frequency earthquakes. And surprisingly, what it does before an eruption is the opposite of what we're conditioned to expect. The seismicity shuts off. It gets very seismically quiet. So for about 3/4 of a year before this eruption started, the seismicity dropped way off, and it was almost entirely gone right before this volcano erupted. So this volcano seems to have read the rules backwards. We've seen, so it's been in an eruptive phase for the past couple of years. We've had some small explosions recently. Again, you see one of these declines in seismicity, and then pop, it blows its cork in a small eruption. And we think now, just in the past few months, it appears to be possibly coming back to a more sustained level that looks maybe something like this. So we think it may be moving into what is apparently its background state. But again, from a seismological perspective, this is a volcano that breaks all the rules. It's fascinating. Okay, the last example I want to talk about is one of the heart-stopping ones. This was an event that occurred in Western Saudi Arabia in 2009. I wasn't involved in this event. A group of my colleagues from the USGS were involved. They went over and worked with the Saudi Geological Survey during this event. So Saudi Arabia is maybe not a place that we think of as volcanically active, but there are occasionally volcanic eruptions in the western part of the country associated with rifting in the Red Sea. And in 2009, there was a very strong and very sudden swarm of earthquakes that began and lasted for several months. Not only was this a very sudden swarm, but these were very, very strong earthquakes. So I don't know if you can read or not, but these are magnitude 5s, magnitude 4s, much larger earthquakes than we typically associate with volcanic unrest. Furthermore, these earthquakes had very, very low frequency. So you'll see, if you can see, they're labeled VLF. This stands for very low frequency. Okay? So this was a very alarming thing when it started to occur. Another thing that was observed partway into this swarm was the opening up of this crack here. Okay? So this was not here before the earthquake swarm started, but the ground actually started to separate. And this is a volcanic vent that's starting to open up. So no magma managed to come out. It's somewhat incredible to me that magma can get so close to the surface, go through so much of this process of opening a vent, and then for some reason stall out or freeze. But this was very close to erupting, and in fact this looked like it was going to be quite a large eruption. The Saudi government actually evacuated 40,000 people from this part of the country for several weeks because it appeared from all of the data that was coming out at the time that this was building up to be a fairly large eruption. And in fact, it did not culminate in an eruption. After the fact, there was a lot of course, sort of post-mortem analysis to try and understand what had gone on, were the interpretations that had been made during this episode of unrest correct. There was an analysis of satellite data, so I talked to you about INSAR, the satellite-based method we have for looking at ground deformation. These are the INSAR maps that are very consistent with this large crack that opened up, so you can see this is sort of the model that's being used to explain this pattern of deformation from the satellites, that there was a fairly large crack filled with magma that opened up in the model by up to 4 meters. And this was fairly close to the surface in the model within 1 kilometer of the surface. So very, very close to erupting. In fact, a failed eruption is the term we use to refer to these types of events.
So there's a dike underneath the surface?
This was a dike that got very close to the surface, a fairly large dike, but no eruption. But treated as one, and really in hindsight, there's nothing we could say that should have been done differently. There was no way to tell that this thing was going to freeze at the last minute. So this happens occasionally, and from a monitoring perspective, these are the most frustrating types of events, the failed eruptions, because there's a big problem with false alarms. They look exactly, and in fact, from a physical standpoint, they are exactly the same thing as an eruption up to that very last minute. So there's just no way to tell which way the event is going to go in foresight. They often trigger evacuations, as did this one. Evacuations are, of course, very costly. They're very dangerous. People do not want to leave their homes unattended. There's a big loss of credibility in cases of evacuations where it turns out to not have been necessary in hindsight. I put up some photographs up here just to demonstrate this from an earlier incident that occurred in California in the 1980s where there was a lot of unrest at Mammoth Mountain, which is a ski area in Long Valley, that culminated in some warnings that there may be an eruption coming. There was no eruption. There was a lot of economic cost to the town, loss of tourism, and people were very upset with the scientists, and there was a lot of suspicion later on that the scientists now were not being honest and straightforward. So these types of events are incredibly frustrating, incredibly difficult to deal with. And one of the things that I work on quite a bit in my research is, well, you know, is there anything we can use to differentiate these episodes from the ones that actually do proceed to eruption? And so far, it's not really clear that there is, that they seem to be exactly the same thing. Okay, so that's one big problem with these quiescent volcanoes, these episodes of non-eruptive unrest. Another question that's maybe less on the hazard side, although there are certainly hazard implications, is what is the relationship of these events to the eruption cycle, to eruptions? So, does a volcano need to go through several of these charging events? I mean, one of my colleagues likened it to a battering ram. Okay, when you hit the door with the battering ram of your medieval castle, you have to hit it a few times before it breaks, right? So is this some kind of battering ram process where for a large eruption, or maybe for a volcano that has particularly strong rock making up its edifice, that there has to be this charging or this breaking process that occurs several times before the eruption can actually occur? And there is some very, very scant evidence that this may be true. A fairly long-standing and large eruption has been going on at a volcano called Superior Hills in the Caribbean since 1995. This has been an absolutely devastating eruption for the economy of Montserrat. It destroyed the capital city. It forced evacuation, permanent evacuation of much of the island. It's a fairly large volume, long-standing eruption, been going on and on, not showing signs of stopping. And interestingly, this eruption was preceded over the century prior to its onset by 3 discrete episodes of non-eruptive unrest, seismic unrest. We don't know what else was there, but there are very well-documented episodes of seismic unrest approximately 30 years apart before this eruption got going. So one question, of course, is, well, were these sort of charging events or breaking events that then led to, that somehow relate to the longevity and the volume of this particular eruption? Similarly, another fairly famous eruption, which was not actually a large eruption in terms of volume, but kind of is on everybody's mind because of the havoc it caused, was the 2010 eruption of Eyjafjallajökull. So this eruption was preceded by several episodes of very clear ground deformation consistent with magma recharging into the mid-crust that did not culminate in eruption. So in 1994 and 1999, the volcano went through these very strong swelling episodes that were consistent with magma being intruded beneath the volcano. So again, was this volcano charging up, and was this essentially the process, the long-term process that ultimately led to the 2010 eruption? And then finally, on an even more speculative note, I want to go back to that quote I gave you from Pliny at the beginning of the talk, where he tells us that there were earthquakes before the 79 Vesuvius eruption, but he makes this interesting sort of offhanded comment about, well, we kind of ignored them because we're used to them. So, of course, one thought, and we'll never know, is, well, was he referring to previous episodes of non-eruptive unrest that then were part of the long-term buildup to the Vesuvius eruption? There's also some evidence in the writings of Seneca about an earlier earthquake in 62 AD. It's actually depicted in this fresco here, or in this relief here in Pompeii, that was centered beneath Vesuvius, and maybe that was also part of a longer-term buildup. So should we be regarding some or all of these non-eruptive episodes as maybe long-term precursors to eruptions, as part of the eruption cycle, what the volcano has to do in the long term before it erupts? Okay, so to sum up, when we look at episodes of non-eruptive unrest beneath volcanoes, we see that they sort of fall along a really interesting spectrum in terms of their depth. So we have deep ones, we have very shallow ones, and also the intensity. So some that are just, that seems to be business as volcano is always restless. Business as usual at that volcano. To somewhere it's all of a sudden very intense, very strong, that's very unusual. It's a departure from normal. We can go a step farther and actually start to put some numbers on a plot like this, and this is where I'm currently working on this problem. Trying to fill this in with data from examples that we have, and you'll see all the examples that I talked about, Harab-Muir, Ileana, Tahoe, and some other ones up here, where we can take the seismicity depths as an indication of depth, and then we can take some measure of intensity, like the total seismic energy that was released during the storm, as our measure of intensity. We can start to plot this out and look at, well, how common are these relative to these? Are there holes in this plot? Where are these boundaries actually? Is there something that gives us a clear indication of which category a particular episode falls in, or does the plot basically fill up entirely? Or do we see maybe levels of depth where there aren't episodes, or levels of intensity that don't seem to be showing up? So this is basically an attempt to sort of examine all of the cases we've had and try and make sense of them in sort of a bigger model of how volcanoes work, how these non-eruptive episodes work, and also how we can interpret them, either in terms of a physical model or statistically, in terms of probabilities for what's going to happen next. We see a certain combination of intensity and depth. So, but as you can see, there aren't a whole lot of points on this plot. It's a very data-poor field, unfortunately, because as I mentioned early on, we haven't had seismic data from volcanoes until most recent decades, and it's still quite rare. So currently, we are very data limited in studying this problem. We only have a handful of examples to look at. Part of the reason for that is because all of the technologies that we have that allow us to look at volcanoes globally are satellite-based. They're not very sensitive. They tend not to pick up the smaller episodes, so we're kind of biased towards the big ones. We do have INSAR, which can pick up very large deformation events. We do have satellite-based gas sensing tools that allow us to pick up very large degassing events. But really what we need is a global network of very sensitive ground-based instrumentation like the seismometers. But of course, these are very expensive. They're very hard to transport and put onto a volcano. And as you saw, they're not very durable in the face of an erupting volcano. So really what we need to do is rethink and harden our instrumentation and figure out how to get around some of these limitations so that we can have more of these sensors on volcanoes, on all of the volcanoes in the world. So I'll just finish up with a few words about a very recent project that we've undertaken in DTM. It's called the Bento Project. This is our attempt to begin solving some of these instrumentation problems, developing a new monitoring system that allows us to use the Iridium satellite network to bring critical data back. We are basically in a field testing phase right now where we're putting these things out on volcanoes, seeing what breaks, bringing them back to the lab, trying to make that better, putting them back out, and then seeing what breaks, hopefully something different, fixing that. So iterating to make something that's much more durable, that can stay out for longer. Ultimately, we're trying to make these low cost. We're trying to make them so that they can send us data back from places where there may be no phone lines, no radio links. We can use global satellite communication systems so that we can at least get minimal information about what's going on at some of these remote volcanoes so we can start to understand this problem a lot better. So this is a very early stage project here at Carnegie, but it's along the lines of our long-standing tradition of instrument development, really cutting edge and pushing the envelope in terms of the instruments we have available to solve these key problems. So this is something I'm extremely excited about, and I'll be doing a lot of traveling this summer to go out and maintain and investigate some of the prototypes that we put out in the field of our bento systems. Okay, so on that note, I just want to briefly acknowledge some of my collaborators on the studies that I've mentioned. And thank you all for your patience, and I'm very happy to answer any questions you might have. Thank you.
Happy to take some questions.
You want to pass the
Sure.
microphone?
That was a terrifying talk. If you had more instrumentation on the ground, would it have been an even more frightening talk?
Yes and no. I think the thing that we learn, the more instruments we put out, the more we see that volcanoes are very alive under the surface. And to me, that's not terrifying. It's fascinating. Okay, well, yes. I might have a different perspective. But that's information. And again, you know, when we see these things, that's what I'm more scared of a volcano that has no instrumentation on it, because we have no way of saying what's going to happen next. So I would say, just in answer to your question, it would be less terrifying. We would know more, and we would be able to say more. And I think we would find that you know, none of these guys, very few of these guys are actually asleep, but you know, we can watch them and we can understand them.
You're probably afraid of asteroids.
This may not be directly related to that, but as a geologist, my question is, do most of the dikes and sills get in place during this quiescent phase, or do they get in place during eruptive phases?
Well, I don't think we know yet. Again, so this comes to this small numbers problem of, we suspect that the bulk of magmatic activity does not have a surface expression in terms of eruption. And we can go to the Sierras, for example, the batholiths, and see that there are just massive volumes of intrusive rocks. So that's just, actually most of it is emplaced underground, and not much of it comes out. Most of it is intrusive, not eruptive.
Right, but does it occur during eruptions, and that it's not, is there more eruptive stuff? But obviously most of it's intrusive, but the question is, when is that intrusion taking place? During an eruptive phase, or is it taking place, you know, in these quiet phases?
I mean, I would say, really extrapolating from what little we know, I would say that just because the intrusive events are more common, most of it is occurring during the intrusive phases. It may be that eruptive phases are eruptive because the volumes are larger. So I don't know that there's really a good way to guess. But if you assume that, you know, an input of magma into a crustal system is the same volume whether it erupts or not, just the fact that the intrusive ones are more frequent would suggest that it happens more during the quiescent phases.
I was wondering if measuring the temperature of the land, they were doing that at Sudac Volcano in 1993, and I don't know what came of it.
We do measure the temperature of volcanoes quite frequently. In fact, at Talika, one of the sensors I've recently put out is a set of thermocouples, and so we often see changes. We see the volcano heat up, basically. We can either measure the temperature directly that way, or we can observe it indirectly by seeing, for example, increased snow melting at the surface of a snow-covered volcano. That's fairly common. So temperature monitoring is actually a fairly common. It's also something we can do from satellites, again with lower resolution. We can do it with ground-based instrumentation. We have now infrared cameras that we can go out and point, take these very cool pictures, so we can actually get maps of the hot spots on a volcano, and it is a very good source of information about what a volcano is doing and whether it's getting ready to erupt.
Thank you. Pretty basic geology question here. How deep do you have to go for all of the Earth's inner content to be the same, magma-wise, and then at what point are there differentiations? You mentioned at one point the type of rock. So at what point on the Earth's layers of surface, the surface layers, is the rock different, and does that impact the type of eruption?
Well, I think what I was referring to was very much the superficial geology. So, for example, if there is a granitic basement, a very competent basement that magma has to work through, that's going to be much stronger than a sandstone or a fairly fractured area of rock, and that would be within the upper few kilometers. So just what I was alluding to.
The final phase of is it going to
the
turn
final
out does depend on that layer type of rock.
Right, but there are going to be differences pretty much as deep as you go. The Earth never gets completely homogeneous as far as we know, but
there's no one core of magma at the center there that's going to go in any direction with the same source, same starting.
yes and no.
Quality.
Once you get into the mantle and into the lower mantle, things do appear to become more homogeneous, but still with variation. But no, I'm referring specifically to essentially surface geology, the upper few kilometers, and how strong that rock is, which is a function of what type of rock it is, and also how damaged it is, how competent it is.
This is probably a harebrained idea, but cell phones are everywhere, and I understand most smartphones have 3-axis accelerometers. So I wonder if there's any value in, see, you're not using your cell phone, you're in a basement, you put your cell phone turned on the floor with a bag of something to weight it down, connect it to the concrete, just to monitor what's going on when you're not using the cell phone.
It's not harebrained at all, actually. There's several projects going on, not at Carnegie, but some of my colleagues are involved, using not necessarily phones, but the accelerometer chips that exist within phones, if you guys have the Wii remote, that's got a little accelerometer in it. Those little accelerometer chips now are getting very inexpensive, and people are working very hard to figure out how to integrate them into seismic sensing technologies. But yeah, I mean, in concept, an iPhone has everything. It has power, it has communication, it has the little accelerometer in it, it has the output. It's kind of a little seismometer, and you can even buy a little app that lets you treat it like a seismometer. You can actually, it's free. But we are trying to do something along those lines.
I guess the catch is, could you calibrate it?
Could you calibrate it, and could you couple it and make it sensitive enough? So if you just put an iPhone with a bag of sand, I've tried this, and stomp on the ground, you might be able to get a signal. But the way that the chip is suspended in the iPhone case is not ideal. So people are trying to essentially take the guts and build it into something that's a little more purpose-built.
So you'd have to rebuild the iPhone.
Yeah.
This sounds really weird, I'm sure. Do you have any concerns about fracking and pouring gas? Not worried at all? Okay, good. So drilling, I have great concerns about interfering. That's what I see it as, interfering with the Earth's crust. Do you have any concerns about such activities, and do you think it destabilizes the Earth's crust, or is it too superficial, too shallow?
Well, we know that human activities can induce seismicity. This is actually a big area of study right now. I was just at a seismological conference a few months ago where one of the big topics was induced seismicity. It's not the fracking itself, which appears to induce seismicity, but the reinjection of the fluids that are used for fracking into the ground that can trigger seismicity. And this is a very active area of study. People are looking at what the relationship is, whether it's the rate of pumping or the volume. It turns out that volume of injected fluid is a big one. So, yes, I mean, I think it's reasonable to be concerned. Another big factor is reasonable to be concerned, and it's something that many people are working on right now to try and understand how do we do it in such a way that doesn't trigger seismicity or interfere in other ways with the Earth's crust, or is that even possible? So I'm, you know.
Do you have insufficient data at this point to say that there's an effect?
There is an issue with obtaining data in some cases in terms of injection rates, injection volumes. This is a state-by-state issue, how much this information has to be made public and over what time scale when it has to be released. So there is the problem of information holding up some of our understanding. But the pace of understanding, and I'm personally not involved in any work on this problem, but just I'm very interested in it, and the pace of understanding on this problem has really accelerated in the field of seismology, because it is something that is very concerning. So people are working very hard on it and really pushing to get the information they need, or going out and collecting it to the extent possible. So yes, I think it's a concern. We don't yet have enough of an understanding to make definitive statements about if and how it can be done safely or unsafely, but it's something that obviously there's enough concern to warrant quite a bit of scientific research right now. It's very much an active area of inquiry.
Next question. Is there a link at all between volcanism and near-Earth objects, comets, and so forth?
Not that we're aware of. There has been in the past some work to understand whether Earth tides can influence volcanic activity. The current thinking on that is no. So basically, the Earth gets squished back and forth, and can that actually squeeze a volcano into eruption? The current thinking on that is that no, those stresses are not strong enough. There very recently was some intriguing data that suggested that actually ocean tide loading might be able to induce enough stress on a magma reservoir that's already at a critical point to tip that reservoir into failure. But near-Earth objects, not really, no. I mean, aside from these large gravitational forces, it's probably unlikely.
Excuse me, thank you. Is there a connection, like if you have an area such as Yellowstone Park with a lot of geothermal activity, is that essentially a volcanic area or what?
Yellowstone is a volcano. It's a special type of volcano called a caldera. It's a very large volcanic system, and there are several of these on Earth. The other big one in the United States is Long Valley Caldera in south central California. So it is a geothermal system, but it's also a magmatic system. It has had very large eruptions in the past. It has the potential to erupt in the future, although we expect that eruption would most likely be very small. It's currently very geothermally active, and that's related to the large residual magmatic system beneath the caldera. So those two things are very much linked, and it's a very well monitored and well studied volcano. But it is calderas in general tend to be very active. They're always restless. They tend to go through periods of unrest, often very large episodes of unrest that generally don't culminate in any surface activity. Probably because they're very large systems and they can buffer any sort of perturbation, a small amount of magma coming in from depth or so on. But the geothermal activity in the park is ultimately related to the magmatic system beneath Yellowstone.
I think we'll stop the questioning there, move on to informal questions. And if you want to see the seismometer down here, it's available. Diane will be available for a while afterwards to answer your questions. This will be the last of our neighborhood lectures for this season. They'll start up again in the fall. So if you're interested in them and you're not already on our mailing list, please sign up on the forums outside, and we'll put you on the mailing list for the next one. And finally, I think we should thank Diana for